Good evening, everyone. My name is Osama Azizi. I'm an intern at Total, and today, on behalf of my tutor Reda Alami, I'm going to present our work on TSGLR and adaptive Thompson sampling for the switching multi-armed problem. So we consider the piecewise stationary Bernoulli multi-armed bandit, which is defined as a three-tuple: first, a discrete set of actions of size A; second, a sequence of time steps going up to t; and finally, the probability distribution of the reward of arm A at time t, which is in this case a Bernoulli distribution with mean mu at. We also consider an unknown number of change points, and we place ourselves in the global switch setting. So our algorithm combines Thompson sampling with the GLR change point detector. At each time step, we play an arm and update its parameters using the Thompson sampling, and we detect a change using the GLR. If a change is detected, we restart the Thompson sampling, otherwise we repeat the process. The Thompson sampling GLR achieves the regret of big O of log t times kt, where kt is the number of change points. So the first question is, why do we use the Thompson sampling? Analytically, the Thompson sampling has been shown to be asymptotically optimal. Therefore, the expectation of the pseudo-cumulative regret reaches the Ley and Robbins lower bound on the regrets for the Bernoulli multi-armed bandit. The second question is, why do we use the GLR change point detector? First, an online change point detector is evaluated using two criteria: the probability of false alarm, and second, the detection delay. For the GLR change point detector, the probability of false alarm can be controlled using the parameter delta in 0, 1. And the detection delay has been proven to be asymptotically optimal, so its upper bound reached the lower bound stated by Ley and T. So equipping the Thompson sampling with the GLR is a wise choice to handle the piecewise stationary bandit. We show the following theorem. So the Thompson sampling GLR regret upper bound is composed of three terms. A first term, which represents the stationary regret of the Thompson sampling oracle, which is the strategy that restarts the Thompson sampling at each change point. A second term caused by the detection delay of GLR, and finally a problem-dependent term, which is related to the cost of focusing on the optimal arm. Analytically, the absolute difference between the regret of Thompson sampling oracle and Thompson sampling GLR is big O of 1. The Thompson sampling GLR hence is very close to the learning strategy restarted at each change point. We test the TSGLR against state-of-the-art algorithms using a synthetic Bernoulli with these parameters, and we average the results over 50 runs. We can clearly see that the Thompson sampling GLR outperforms state-of-the-art algorithms by achieving the minimal pseudo-cumulative regrets. We also validated the Thompson sampling GLR using a real-world environment, and in this case we used the Yahoo users click log dataset. Again, in this case, the Thompson sampling GLR beats state-of-the-art algorithms. So as a conclusion, in our work, we constructed a non-stationary multi-armed bandit strategy that is optimal in the piecewise Bernoulli global switch setting, and we validated our approach in both a synthetic and a real-world application. As a future work, we are planning to extend the algorithm to the per-arm switch setting, and for this purpose, an extra exploration step should be added to detect changes in suboptimal arms. Thank you very much for your attention, and don't hesitate to reach out if needed. Thank you.